So now that we're kind of in the second week of the class, and I've given you a little overview about Java 8 functional programming, and hopefully given you a little motivation to go back and remember the object-oriented programming that you've learned in earlier courses or can pick up on your own very quickly, it's now time to start really focusing on what the class is about, which is parallel computing. And so we'll still spend a little time later on some other kind of non-parallel features in Java 8. Particularly, we'll talk about Java 8 sequential streams down the road in a couple weeks. But this is the time to transition into the real meat of the course. So what we're going to talk about here in the first part of this lesson is what the heck do we mean by terms like concurrency and parallelism. I've been kind of using them a little loosey-goosey so far, but I'll tighten up the definitions of them, and you'll see how they compare and contrast. And we'll start with an overview of concurrency. So concurrency is a form of computing where threads can run simultaneously. So what the heck does that mean? Well, first, let's kind of take a little bit of a look at some notation. The gray round angle here is going to be a process. And process, for those of you who haven't taken an operating systems course yet, is essentially a unit of resource allocation and protection. So if you have taken an operating systems course, then you're probably familiar with a Linux or a Unix process or a Windows process, basically the context in which programs execute. And within the context of a process, you can have one or more threads. And that's also what this diagram shows as well. So you can see the little squiggly lines, that's supposed to be like a thread, and the little arrows like a program counter keeping track of where we are in the thread and so on. So that's the big picture view. So a thread in Java is a unit of execution for instruction streams that can run concurrently or in parallel, as we'll see later, on one or more processor cores. So here we've got some number of processor cores. That's what the little Apple cores are supposed to be representing visually. And we've got some number of threads, and at runtime, the operating system and the virtual machine and the OS kernel and so on will make sure that these threads are mapped. Each of the threads gets mapped to a core where it can run for some period of time before it gets swapped out, or if it gets paged out, or it gets suspended, or whatever the right term is. I guess it's context switched is the right term. So the threads can run for a while, and then they get context switched out after their scheduling quantum elapses, and then some other thread can get a chance to run. Yeah. A core is just a unit of computation that could be implemented in hardware. So modern processors, for a variety of reasons, have a lot of cores, or have more cores than they used to. They usually have multiple cores. And so each core is kind of like a little mini instruction processing unit, and a computer chip, like an x86 chip or a chip that's done by a PowerPC chip or whatnot, they'll have multiple cores that can run in parallel. So it's just a way of executing your program instructions, or the binary representation of the program instructions, in some kind of little mini processing unit. And there you'd have multiple cores per chip. Does anybody know why we have lots of cores these days? I think we talked about it very briefly the first day, like the first couple slides. Why do we have lots of cores at the moment? Moore's law, right. Moore's law basically says that every 18 to 24 months, the number of transistors on a chip doubles. And that's been going on for a very long time. For a long time, in addition to doubling the number of transistors on a chip, the clock speeds were also doubling as well. And then about 2003-ish, middle 2000 time frame or so, that aspect of Moore's law sort of petered out. So it's no longer the case that we're doubling the clock speed. The clock speed has remained roughly around 3 gigahertz, give or take, for about a decade. However, the number of transistors on a chip continues to go up at Moore's law. So rather than relying on the clock speed to make programs run faster, nowadays we just put more cores. We use the transistors to make more cores on a chip. So back 10 years ago, dual core was what you would typically get. Nowadays, quad core is very, very common. In fact, my mobile phone, my Android mobile phone, has quad core processor in it. That's very common. My laptops have quad core processors. I wouldn't be surprised in the next couple of years we'll have octo core processors, very common. And even today, servers often have 8, 12, 16, or more cores. And that's what we're doing with all the excess transistors, is we're putting more parallel processing units on the hardware, on the chips. And I'll talk about that in a second, because that makes it figures in very prominently as to why Java 8 and beyond is defined the way it is in terms of the processing and parallelism models that they provide. Did that answer your question? Okay. So the threads map to the cores, and the cores are actually what physically run the processing in parallel. And how do you make a thread? We've seen some examples. You would say new thread, and you'd give it some computation to do its thing. Now, in concurrent style programming, if you're running concurrently, the most common use of multiple threads is to allow the user interface thread to focus on interacting with the user. That's why it's the user interface thread. And to offload work for longer running computations to one or more background threads. So a very common concurrency architecture in almost all, and probably all, modern user interface driven platforms like iPhone, like Android, and so on, is to have a separate thread called the UI thread, or the user interface thread, and that's responsible for interacting with the user and displaying the results and so on. And any user interactions go in the UI thread, and then any longer running computations like downloading a file or doing some kind of long running database operation, or waiting for something to finish that takes a long time to run, like decompressing a file or something like that, decompressing an image. Those things are done by threads that run in the, quote, background. So that's the basic idea of modern concurrency. And the constraints on this process are that the background threads, because you can have multiple of them, they can afford to block, which means they can wait for something to happen. In contrast, the user interface thread, or the UI thread, is not able to block, or if it blocks, it blocks for infinitesimally short periods of time, like a second, maybe. So you really don't want the user interface thread to ever block, and you want the background threads to be the things that block. And that's why you need multiple threads, because you can have long-running computations taking place in the background, and they can afford to block to their heart's content, and the user interface thread never has to block. Now, that, of course, raises a whole bunch of interesting questions. How do you do this? How do you communicate back and forth between background threads and the user interface thread, and vice versa? And modern user interface frameworks for smartphones and other devices with these types of constraints solve that problem in various ways. And we'll talk a bit about that later. In particular, Android has a couple of cool frameworks called handlers, messages, and runnables, or the Hammer framework, hence the hammer. And they also have another framework called the async task framework. And that's how they structure communication between the user interface thread and the background threads. We're actually not going to talk a whole lot about that, but that's just some context for you. Now, once you've got all these threads running around, there's a bunch of different ways for them to interact with each other. And the two primary models, or paradigms, just a fancy name for a model, are shared objects and message passing. So we'll take a look and see the different approaches. Shared objects are kind of the classic way of doing things. And the way it works is if you have multiple threads that need to coordinate their actions, they do so through an object, and this is sort of just a regular old Java object in Java, that is carefully designed to be able to synchronize access to the internal state of the object. And why do we need to do this? The reason we need to do this is we want to make sure that that internal state is not corrupted because multiple threads, possibly running on multiple cores, all came through and manipulated the data at the same time, either updating it or reading it or other things. And so this is a little picture that kind of visualizes this. This is an example of what we might call a monitor object in Java. And a little known fact, or actually a very known fact once you know it, all Java objects have the potential to be monitor objects. You just have to program them correctly. And the basic idea with a monitor object is only one thread at a time can be active inside the object itself, updating or accessing the object's state. So you'll have some state internally, and that portion where you can be running is what's called a critical section. Critical section means that just one thing is allowed to be there at a time, because you could be modifying state or making changes to the state of the object. And any other threads that would like to get access to the parts of the object need to queue up and wait their turn to get into the critical section. This is often called mutual exclusion. And I think I gave you a simple example that will be memorable, which is a restroom on an airplane where you have a line of people waiting to go into the critical section, and only one person or one thread is allowed in at a time. And you basically have this lock, which is either vacant or occupied. And the rule is, if it's vacant, you can go in, you shut the door, you lock it, now nobody else can get in. And when you're done, you leave and you release the lock. That's often called fully bracketed synchronization or fully bracketed locking. All right, so that's kind of the classic way that people write concurrent programs. They have objects, like in Java, monitor objects, and they synchronize access to the internal state of the object. Now, it turns out that there are a lot of different ways of doing this in Java. You've got the concept of synchronized statements, synchronized methods, you have reentrant locks, you have atomic operations, you have semaphores, you have condition objects, you have lower level mechanisms like compare and swap operations that are available kind of at the JVM and hardware level. So there's no end of things you can do to synchronize stuff. And you can look at this article to get an overview of some of the things. So we've got sort of mutual exclusion, locks, which is like the restroom in an airplane. We have things that allow you to kind of coordinate or interact, synchronize between things, and so on and so forth. So there's a bunch of different ways you can do stuff in Java. Ironically enough, we are not going to talk about almost any of that in this course. If you're interested in these topics, come back in the spring, and I teach another course where we spend a lot of time on these topics. So that's a way to give you the full, comprehensive perspective on concurrency and parallelism. But this is a parallelism course. The second paradigm that you can use to interact between objects is by sending messages. It's called message passing. And what you do here is you have one thread that wants to tell some other thread to do something, and the way it does it is by creating a message and then passing that message to some other thread through a thread-safe queue. And here's what a thread-safe queue typically looks like. You'd have one or more threads that are putting elements into the queue, and one or more threads that are pulling stuff out of the queue and doing something with what they receive. And the trick is to implement the queue correctly, and typically it's implemented using something called a blocking queue. And all that means is if you try to enter something into the queue and the queue is, quote, full, then you block until the queue is not full. And likewise, if you try to take something out of a queue and the queue is empty, then you can block until the queue is not empty. So that's a 10-second explanation of message passing. Yeah? Great question. So the question is, what's the relationship between the blocking queue and things that are trying to put stuff in and out of the blocking queue? So it's obviously up to you, the programmer, or you, the architect, to decide what those relationships are. As we'll see, there's a lot of different kinds of thread-safe queues in Java. So we have things called array blocking queues. We have things called linked blocking queues, which, surprise, surprise, use an array or a linked list as the queue implementation. And in that case, you could have one producer thread and one consumer thread, or you could have a group of producer threads and a group of consumer threads. It's really up to you how you allocate the threading architecture with the blocking queue. And the way it works, of course, is it'll work in either case. If you know you only have a single producer and a single consumer, there may be more efficient ways than using some of these more generic approaches. There's priority blocking queues, which order things by their priority. So whatever goes in, you could go in to the queue in any order, but it's the priority that assures how they come out of the queue. There's things called synchronous queues. There's concurrent link queues, lots and lots and lots of queues. Once again, we will hardly talk about these topics in this course. That's a great topic that we'll cover in detail this spring. So irrespective of whether you have shared objects or you're using message passing to interact, the key thing is to make sure that you exchange the information and coordinate the concurrent processing safely and efficiently, and you avoid various hazards. So let's take a look at a couple of the hazards. So one very classic type of hazard is something that's called a race condition. And a race condition occurs when two or more threads try to simultaneously access state in an object in a way that's not properly synchronized or not properly locked. And in that case, the outcome of the program will depend on the sequence or timing of the threads. So if you get lucky and one thread comes along and nobody else is doing anything to the object and it updates it or it reads it, and then later another thread comes along and it updates it and it reads it, you might be fine. Or if they both show up at the same time, which happens increasingly frequently in multi-core processors, because you've got things literally running in parallel, then you're going to have problems. You're going to have race conditions. And race conditions are maddeningly difficult to track down. If you're not really familiar with what a race condition is, you might want to play around with this little test program I wrote called buggy queue. As the name implies, a buggy queue is buggy. And so what it does is it has a queue that we're using to pass messages back and forth, but it has no synchronization at all. And then it allocates a couple of threads, one reading and one writing, and then they stomp all over each other's access to the state of the queue, and it corrupts it. And if you run the program, it'll blow up and give you very strange results, demonstrating that race conditions are easy to occur. So race conditions happen if you have what's called shared mutable state, which is the root of all evil in concurrent programs, in parallel programs. Another related problem, although slightly different, is something called memory inconsistencies. This is a little bit more difficult to explain. I won't spend a lot of time on it right now. We'll cover it in detail in the spring. But in a nutshell, modern multiprocessors have multiple cores, and each of the cores has its own memory cache. And there's a reason for that. You can read the memory out of the cache very quickly. So if you have a bunch of threads that are processing and they're not trying to share or coordinate between other threads or other cores, then these caches make things run really fast. The problem arises if you've got multiple threads trying to access a common object, in which case the object's fields will get cached in the caches in each of the cores. And therefore, if somebody's writing or reading from something and it's not properly synchronized, you'll end up with inconsistencies between the view that one core has of that object state and the view that a different core, different thread has on the same object state, which is not coordinated. And so all kinds of crazy things happen. And so this is a very, very subtle and complex topic. I'm not going to talk about it much here, but the way to think about it, sort of intuitively is, if you're a Star Trek fan, you can have the transporter beam, right? And the transporter beam really needs to be atomic, because you don't want to beam like the person's legs someplace and keep the upper body someplace else. That would be bad. If you're not a Star Trek fan, and so that example makes no sense, but you're a Harry Potter fan, remember splinching? So if you apparate, right, and you apparate incorrectly, you can end up with your nose sticking behind and you go somewhere else. Same kind of problem. You want these things to be atomic. So memory inconsistencies occur because modern systems cache a lot of stuff. So unless you take steps to the contrary, it's possible to have inconsistent views of what should be the same data. Once again, I'm not going to talk much more about that, and you'll learn why we're not going to talk about this stuff later, because the wonderful parallelism frameworks in Java 8 make a lot of these problems just go away for the most part. Yet another problem that occurs with sharing of information between multiple threads through objects is something called deadlock. And deadlock occurs when there are multiple threads competing for some resources, and the way in which they compete leads them to end up with what's called a circular embrace. So nobody actually gets what they want, and they just wait forever. Here's a very simple example. Let's say we have two threads, T1 and T2, and we have two locks, L1 and L2. And let's say, for sake of argument, because of the concurrent non-deterministic nature of the processing, thread T1 owns lock L1, so it's the owner of the lock. T2 owns lock L2, and now T1 needs to access L2, and T2 needs to access L1. And if you have that kind of a set of dependencies in the ordering of resources, then T1 will wait forever for L2, which T2 owns, and T2 will wait forever for L1, which T1 owns. And that's what's called deadlock. And concurrent programs are very prone to deadlocks. There's lots of ways around this, but that's another very common problem in concurrent programs. Okay, so that's basically a very quick overview of concurrency. Having said all those things, we're not going to spend any more time on concurrency in this course for the most part. So now you have 10 to 15 minutes worth of concurrency knowledge, just enough to be confused. If you really want to be unconfused, come back in the spring and we'll explain it in a lot more detail and you get a lot more chance to practice with it. The reason why we're not focusing on concurrency is because we're going to be focusing exclusively on parallelism. And it turns out in Java 8, there's some really good support for parallel programming, which makes many of the problems I just talked about disappear as long as you follow a few simple rules. But of course, that raises the question, what the heck is parallelism? Especially as what's the heck of parallelism relative to concurrency? So parallelism is a form of computing that performs multiple steps on multiple processor cores. And so here's the basic idea. We've got this set of cores, maybe the same set of cores we had before, but now we're going to do something different to the processing sequence. In particular, we're going to start by taking the overall problem to be solved, and we're going to partition it or fork it. That's the funny word, fork. When you ever hear the word fork, think split or partition. We're going to partition an overall task up into a bunch of subtasks, into chunks of subtasks. So that's part of what we do. We break a big problem up into small problems. The next thing we're going to do, once we've got all the problems sufficiently broken up to where they're atomic, we don't want to split them any further, we can then take all those subproblems or those subtasks and we can actually run them. Each task or each subtask runs sequentially, but together they all run in parallel. So we have a bunch of sequential tasks running at the same time. Does that make sense? So sequential things are all running in parallel. And they're sequential because we haven't broken them up anymore. So a particular thread will do some processing. And that processing will be done on different parts of the overall problem we're trying to solve. So different subtasks will run in parallel as part of the overall task processing. All right, so far so good. We took a big problem, we split it up into parts. Each of those parts is now running in parallel, sequentially. And then we've got to combine it all back together again. We've got to take the sub-results from the subtasks, and we have to join them or merge them or combine them back together again in order to produce some final result. So this split, apply, combine model, which is sometimes referred to as map-reduce, but we'll talk about that later, that's basically at the essence of what parallelism is all about. Now, the goal of all this is to do the splitting and the applying and the combining very efficiently so that we actually get a win, right? It doesn't do much good to do all this splitting and processing and combining and so on if the end result will be slower than it would have been in the first place. And ironically, there are actually fairly large number of problems that don't parallelize very well, sadly. But our goal in this class will be to see how to learn how to parallelize things and then how to use the Java parallel frameworks in order to make them run faster. So you can basically think of parallelism as an optimization whose goal it is to increase throughput, scalability, and reduce latency. So you want more work to be done in any given unit of time because they're running in parallel, and you want the time required to get something done to go down because everything's going at the same time. And so I like to use my metaphor here where the volume goes up to 11. Does anybody know what that's a reference to? Spinal Tap, right? Yeah. So if you haven't seen the movie Spinal Tap, it's a classic mockumentary of a rock band done about probably 20 years ago or more. It's really funny. And one of the recurring themes there is that the guy has an amplifier that goes up to 11. So he says it's louder than amplifiers that only go up to 10 because it's one louder. So if you haven't seen the movie, it's great. Parallelism works best when the threads that do this parallel processing share no mutable state. What the heck is mutable state? Mutable state is simply state that's able to be mutated, able to be changed. And if you read this blog posting, you'll learn why mutable state, or rather shared mutable state, is the root of all evil in concurrency and parallelism. So we want to avoid sharing mutable state. It's perfectly fine generally to share state, just not mutable state. So you can have read-only state, that's okay, but you don't want to have read-write state. There, of course, are exceptions to this, but that's the goal. It works best when you have those conditions. And the second thing you'd like, and this is sometimes easier said than done, is you'd also like these threads that are running to not have to block. You want them to be so-called run-to-completion tasks. Again, sometimes easier said than done, and I'll talk a lot more about that as we get further along. So things work best if there's no mutable state and things don't block. If there is mutable state and there is blocking, there are certainly ways to make this model work. It just takes a little extra effort, and it may not scale up as linearly as if there is no mutable state and there is no blocking. So it's possible to do it, it just takes extra work. And this is significant. The reason why I even mention this at all is when we get into the next part of the course, after we're done with this introduction, we're then going to talk about the first real programming framework, parallel programming framework, and you get a chance to do some programming assignments with the first programming framework. And the first thing we're going to focus on is the fork join pool. And so Java has this thing called the fork join pool. And one of the things that the fork join pool does is it does work stealing. And so we'll talk about what work stealing is and how it works and why it makes things scale up. So you could take a look at the fork join model, which talks about the model of parallelism that Java's fork join pool implements. And you could also take a look at work stealing. If you're curious, of course, we'll cover all this stuff throughout the next few weeks. There's a really great tutorial by a guy named Brian Getz, who is a senior architect for Java. And if you go to this link, you can watch it. I really recommend you watch it. It's very, very good. It's probably about an hour long. And he explains the transition in Java from concurrent support to parallel computing. And one of the main points he makes in his video, which I just excerpt here to get the point across because it's really crucial to an understanding, and it actually goes back to the conversation that we talked about earlier about why we have lots of cores these days. His explanation of why they made that evolution from concurrent to parallel computing is because we run into this sort of weird software-induced bottleneck where we've got lots and lots of cores now, but we actually haven't gotten the speed up that we would have liked. So this is what we thought we would get. We would think as the number of cores go up, we get sort of, as the number of cores increases by Moore's law, we'd expect to have performance going up accordingly. But what's actually happened is the number of cores have gone up, but the actual speed up hasn't really improved. And the reason for that is because most people are not comfortable programming concurrent software efficiently and correctly. It's a very hard thing to do. So in Java 8, they introduced a new model, which is combining functional programming, all the stuff we just talked about, right, like lambda expressions and method references and functional interfaces, in conjunction with their cool fork join framework to give us efficient fine-grained data parallelism. And the combination of those two things makes it easier to write programs that scale. And I'll show you examples of that as we go through this. OK, so that's a quick summary of concurrency and parallelism.